We are the Additive Manufacturing Group, and we will be focusing on designing and analyzing a connecting rod for a light-duty combustion engine. Additive manufacturing is the process of building a 3D object by depositing material, layer by layer, until a desired geometry is obtained. The process is typically done using computer-controlled machinery to precisely deposit material. Some common materials are plastic, ceramics, and metals. The type of additive manufacturing we will be using is called selective laser melting. This method is used primarily for metals, but similar concepts can be applied to plastics. To begin, oxygen is evacuated from the build chamber and replaced with an inert argon gas. Then, ultrafine metal particles are spread very thin over a build platform. A laser welds the metal particles in selected areas to the base material underneath. After the welding sequence is completed, the build platform moves down in the negative Z direction, and a new layer of metal particles is spread over the build platform. The process repeats until the part is complete. After the part is done printing, the excess powder is removed and recycled, and the part can be separated from the build plate.
For our motivation and purpose, we first analyze the difference between additive manufacturing and standard manufacturing. Additive manufacturing is the new developing technology that adds precision and eliminates material waste compared to the subtractive nature of traditional manufacturing. For this reason, our goal was to provide a functioning project to further support the benefits of this technology. We had the chance to learn in detail what SLM was and power bed fusion, which is also useful to know in the manufacturing industry and as an engineer, being that we're in charge of the creation process. Lastly, we used our SolidWorks and ANSYS skills to demonstrate if the part can be made through additive manufacturing.
We first model our connecting row and the substage in the SolidWorks with 1 inch thickness, and then we assign 17-4 pH stainless steel to both parts, because when we find the research, we find out this material has a higher material strain, and it can operate for a longer life cycle under high pressure and a high repeatability process. Especially for the engine, the roll is encounter rotation consequently, so it would be the best fits for our situation. Then we also made the assumption for the thermal process. We first ignore the convection and radiation heat transfer inside the view part, because compared to the conduction, it's really small and basically can be directly ignored. And to simplify the question, we also assume the material is homogeneous and isotropic, which means the row should be uniform and also have the identical values of the property in all directions. We also ignore the boundary fat of the build part to simplify the question, and then apply 70 degrees C to the bottom of the base plate. So heating the bed, because it's really would dramatically improve the print quality and to avoid warping. So warping in 3D printer is commonly happen because it's the uneven cooling rate, and so without initial heat, if we don't apply 70 degrees C over here, our model will easily encounter the warping and deform, especially in the edges. Then we jump into the equation. So for any element belonging to previous sinter layer, heat transfer takes place due to the conduction through both its bottom and the top surface. The moving heat sources is stimulated within the model by transiting it in discrete time step, where BD is the diameter of the energy sources, and then V1 is the scanning speed of energy sources. And then we find the governing equation for the 3D heat transfer between the layers and the substrate. As you can see in this equation on the left hand side, the lambda is the temperature dependent thermal conductivity, and the T is the temperature within the part at any time. And then we convert the general governing equation into a metric format, into a finite element formulation. For the first one, we can see CE will be the element specific heat metric, and TC dot, that will be the change in nodal temperature with respect to time. We also determine the KTH, that will be the element diffusion conductivity metric, and the TE will be the nodal temperature in the element. So for the following two equations will be the detailed formulation to get both KE and the CE. So basically here we have the density as a rho Pn, and then we also have the Cp as the specific heat of the part material. And for the N, that would be the shape element vector. For the equation Ke, we got big M as the shape function derived metric. As you can see, there's also a gamma over here. The gamma represents the material thermal conductivity metric. It can be expressed as this one. And for the thermal structure part, we made the assumption we have to fix base of the plate at both bottom and the top. And then we apply 2-pound forces at the center of the mass. This is a simulation of the node when it's printing. It's also in the negative z direction, as you can see in the picture. And then we assume there's no cracking or fracture occurs during the printing process. And then we also give a frictionless support around the base plate so it doesn't move during the printing process. For the equation, we have a general equation. It's Ke times U minus FTH equal to Me U double dot. So in this equation, the U small u, that would be the element stiffness metric, and the Ke, that would be nodal displacement vector. It's expressed like this one. And for the E, that would be a thermal load vector. And the Me, that would be the element mass metric, as well as the U double dot, that's the acceleration vector. So we got the general equation, and then we go into split it into a detailed equation to find each part of this equation. So Ke, that's the displacement nodal vector. You can find the N as the shape function metric, and then this one for determine the thermal load vector, we can find the B as the strain displacement metric, as well as D as the elastic stiffness metric. So lastly here, as you can see, there's another element, epsilon th. That's the instantaneous thermal strain vector for any element within a layer. We can express like this, the equation at the bottom, where T reference is the reference strain free temperature, and the alpha will be the temperature dependent thermal coefficient of the metal. When we finish the equation setup, we go into the building setup in the AM process in ANSYS. So this table is the general setup, numerical setup for our situation. We have the hash spacing as 0.13 millimeter and the scan space as 12,000 millimeter per second. And the rest of the value will be exactly same as the demo video we got in the lecture. And this table is also just following the same step. As you can see, we have the meshing as 0.125, and there's even a smaller meshing for the connecting rod. So we just want, because we focus in the connecting rod, we want to get a more accurate and precise result in the connecting rows, and then we also don't want it to take too long, so this is the element size we determine. For the case 2, where we're going to compare, we just arrange the hash space to smaller, is to 0.07 millimeter, and we also decrease the scanning speed to 800 millimeter per second. This is the general setup table. Lastly is the issue we encountered during setting up our project. So basically, we want to include the conversion at the beginning to determine the meshing size. However, we follow the lecture video, it's the structure analyze video in the lecture. So it should be a conversion tab under the insert after solver is complete, but we didn't find it in here. So we basically just take the meshing size as they in the lecture video, which is 0.125 as well as the 0.0625.
After simulation, the manufacturing time increased by 1281 seconds, or slightly over 21 minutes, from setting 1 to setting 2. As seen on the image, the max deformation occurs at the rectangular corner, forming an upward deflection. The study also shows a 0.001 inch increase. For the structural analysis, we found the max stress was almost 144,000 psi for setting 1, and slightly over 151,000 psi for setting 2. For the thermal analysis, the hatch spacing had little effect between the two settings. As seen on the graphs, the temperature reached 2,561 degrees Fahrenheit in both settings. The image shows the thermal pattern through the process.
Hello, this is Santos Alvarado, and I'd like to bring up some key points of discussion. The first being print performance of this part, that is how well this part is made without warping and deformation, as long without excess stress. And that's going to be dependent on material, the geometry, and the selective laser melting machine settings. And that is the purpose of our ANSYS analysis, is to determine if we can successfully manufacture this part using this method, which in turn should reduce scrap rate because we have a method of doing analysis on our part before we manufacture it. Another thing to consider is the finite fatigue life of these types of parts. Given that they're made in the SLM machine, the porosity, there's going to be a great porosity in that metal. However, there are some methods to improve that. So if you look to the right, you'll see a figure, and on the left you'll see a metal part, the grain structure of a metal part as built, and in the center you'll see the grain structure of an annealed metal part, and on the far right you'll see the grain structure of a part that has undergone a process known as hot isostatic pressing. And that process is where you take the part and you put it in a pressurized heated gas chamber for the extended amount of time to get you a robust grain structure like this. So you can see the figure on the far right has the most robust grain structure, which in turn means a greater fatigue life. And an ideal use of a SLM piston rod like this would most likely be in a high performance vehicle that undergoes usual maintenance, because we do not have any method to ensure an endurance limit. So this would be great in a field such as racing. So in conclusion, the purpose of our ANSYS analysis was successful because we did determine that this piston rod can be manufactured through this method. And some key things to note is that in configuration 1 of the selective laser melting machine settings is that the max stress is at 143,000 psi. And in configuration 2, the max stress is 128,000 psi, and there's also a reduced max deformation of 5%. And this is a result of decreased hatch spacing, which also means an increased printing time.